Tonight, we slip beneath the skin of the ordinary. The bright tip of knowing fades, and enter the blue heavy body of the iceberg where wonder waits in the dark. Not to argue with anyone, not to prove a point, to feel that first electric hush when the mind meets something it cannot shrug off. Here, facts don't feel like homework. They feel like stars seen from a ship's rail. Cold, exact, and a little impossible. Imagine a midnight museum with no plaques, only doors that open when you breathe slowly. Behind each door, a single lucid strangeness sits on velvet. A fact you can touch with your attention. Cool to the fingers, precise as a watch, unhurried as tide. You do not have to memorize it. You only have to let it change the air in the room. Face the phone down. Dim the walls into silhouettes. Listen for the smallest sound left in the house. Let curiosity lower its voice. Let certainty loosen its jaw. If a question arrives, we will cradle it for one breath, set it gently on a shelf, and drift on, calmer than before. Before we begin, let us gather our little midnight crew. If these voyages bring you ease, a gentle like or a simple subscription helps this calm reach others still awake. Tell me the hour you are drifting tonight in the comments, whether that may be midnight, 2 a.m, or even dawn's edge, so I can chart our resting constellation and time future journeys to meet your night. And if you want to sink deeper, the Midnight Voyager playlist is waiting. Now, allow yourself to settle. Let the breath fall in and out, unforced. We are going fact by fact now, one clear facet at a time, letting each cool the mind and widen the room. When you are ready, we begin a calm voyage through truths that feel impossible, and somehow make rest easier to find. The night parts like a slow curtain. A pale door glows ahead. We cross the threshold, and Fact 1 rises cool and clear, like a small star in your palm. The number that sounds impossible is simple to say. The universe is about 13.8 billion years old. Yet the farthest edge of what we can see, the radius of our observable universe, is about 46 billion light years away. If light has been travelling for only 13.8 billion years, how can the source now be that far? The answer is quiet and precise. While the light was on its way, space itself was growing. Begin with light. Through space, light always moves at the same speed. What changes is the scale of space. Picture a long stone corridor, paved with square tiles. You start walking toward a far archway. Your steps are steady, but while you walk, each tile very slowly widens. You do not feel a single tile stretch under one footfall, yet the entire passage lengthens during your journey. When you reach the arch, the distance behind you is greater than your step count alone would imply, because the floor expanded beneath you. In the cosmos, your steady walking is the light's steady motion. The widening tiles are the changing scale of cosmic space. Astronomers separate this story into two helpful measures. Look-back time is the age of the light that reaches us. It tells us when those photons began their journey. Distance now, often called co-moving distance, is how far the source sits from us today, after the tiles have continued to widen. Light that left when the universe was small arrives in a universe that has grown. Both statements are true at once. The journey took 13.8 billion years. The present-day separation is about 46 billion light years. This slow widening leaves its fingerprint on the light. As space expands, the crests of a light wave are drawn farther apart. The wavelength lengthens. The colour glides toward red. This is cosmic redshift. The light does not tire. It is carried on a floor whose tiles widen beneath it. In calm words, the factor by which the wavelength has stretched equals the ratio of the universe's scale today to the universe's scale at the moment the light was emitted. You can hold it without symbols. The more the floor widened during the trip, the redder the light becomes. The scale factor is simply a ruler woven into space, a ruler whose tick marks drift farther apart as time passes. The rate at which that ruler grows is called the Hubble parameter. It tells you the fractional growth rate of the cosmic scale at a given era. Today's value, the Hubble constant, sets a characteristic length called the Hubble radius. which is the speed of light divided by the Hubble constant. That distance is about 14 billion light years. It is not a wall, it is a now scale, the distance at which, right now, the recession from expansion matches the speed of light. Light can and does cross that radius over cosmic history, because the growth rate changes with time. 3 distances make the picture feel complete. The particle horizon, our observable radius today, is about 46 billion light years, the farthest place from which any light has had time to arrive since the beginning. The Hubble radius is about 14 billion light years, a measure of the present expansion rate. And because the expansion is currently accelerating, there is a softer limit called the cosmic event horizon. Regions so far away that light emitted by them now will never reach us, no matter how long we wait. Its size is on the order of a few tens of billions of light years, comparable to, but distinct from, the Hubble radius. None of these are barriers. They are different ways of drawing circles in an expanding room. Why 46 exactly? Not from guesswork, but from history. The universe's expansion rate has changed over time. In the beginning, radiation dominated. Later, matter's gravity slowed the growth. More recently, a smooth energy component, dark energy, has begun to accelerate it. The proper distance to a very old source today comes from adding up that whole expansion history, a calm accounting of how quickly the tiles widened at each moment while the photons were en route. Do that accounting using our best measurements of the Hubble constant, of matter and radiation, of the steady pressure of dark energy, and the present-day radius of what we can see comes out near 46 billion light years. You can anchor this arithmetic with the oldest light we can observe, the faint afterglow from when the universe first became transparent. Around 380,000 years after the beginning, the hot plasma cooled enough for electrons and protons to settle into neutral atoms. Light, no longer trapped by frequent scatterings, could travel freely. That ancient light reaches us today as the cosmic microwave background, a nearly uniform bath at about 2.7 Kelvin, cooled into microwaves because its wavelengths have been stretched by the expansion for nearly 14 billion years. Its tiny ripples, temperature variations of only 1 part in 100,000, are fossil imprints of the universe's first small irregularities, the seeds of galaxies to come. When we map those ripples, we are reading the early ticks of the ruler, the first notes of the corridor's widening. It helps to feel how motion and expansion are not the same. Galaxies do not need to race through space to separate. The fabric between them lengthens. Locally, gravity can hold things together. The Milky Way and Andromeda are bound. Stars orbit within galaxies. Planets circle stars. On very large scales, where no single cluster's gravity rules, the expansion wins. That is why a distant galaxy can appear to recede from us faster than light without breaking relativity. Nothing outruns light through space in its own neighborhood. Instead, the distance between neighborhoods increases because the ruler's ticks drift apart. 2 questions arrive often and are kind to answer. Where is the center? Nowhere and everywhere. In the standard large-scale picture, homogeneous and isotropic space, every observer sees distant galaxies recede in the same way. There is no privileged tile marked "Begin here." What does space expand into? Into nothing beyond itself. Expansion is not motion into a surrounding room. It is a change of scale within the fabric. The corridor has no outer hallway. Only the spacing of the tiles changes. If you like one more firm grip without symbols, hold this. To find today's separation to a distant source, imagine summing, moment by moment, the speed of light multiplied by tiny steps of time, and dividing each step by the scale factor appropriate to that moment. Add those contributions across cosmic history, and you recover the gentle fact that a 13.8 billion year light journey corresponds to a 46 billion light year separation today. Let the ideas settle into shapes you can keep. Look back time is the age written in the photon. Co-moving distance is where the source sits now on the ever-widening floor. Redshift is the softening of colour that records how much the floor changed underfoot. The Hubble radius is a measure of the present expansion, not a wall. The particle horizon is the current limit of what has had time to reach us. The event horizon is the far line beyond which light launched now will never arrive. None of this asks you to hurry. The shapes are large, the moves are slow, the room is patient. Breathe in and picture the corridor not as a trap, but as a comfort, a place whose size you can name, whose growth you can describe, whose light carries its own travel diary. Breathe out and let the numbers soften into trust. The impossible-sounding 46 is only the sum of many small widenings, while the photons were on their way. As you grow heavier in the quiet, let one last thought arrive smoothly. Those tiny ripples preserved in the earliest light, the faint grain of the microwave background, were once almost nothing at all. Yet under gravity's long hand, they swelled into galaxies, clusters, and the great filaments between them. That is where we turn next, from the size of the room to the patterns inside it, from smooth early notes to the music of structure. For now, rest with the picture of a universe that grows while light travels, steady as breathing, calm as sleep. Let your attention rest on a picture that begins almost impossibly small. At the very start, when the universe was young beyond imagination, everything was hot, smooth and bright. Yet even in that brightness there were soft jitters, microscopic fluctuations in energy and density. The quiet background tremble that quantum physics says is always there. They were not patterns you could draw, not bumps you could point to. They were more like a faint grain within the glow, everywhere at once, nowhere in particular. Then came a brief, extraordinary growth spurt. Space itself expanded at a furious rate, not as a wind, but as a change of scale that raced ahead of any signal. This episode is called inflation. It took those tiny quantum jitters and stretched them to cosmic sizes, the way a gentle swirl in a drop of paint becomes a broad band when the canvas is pulled. A wrinkle that was once smaller than an atom became a gentle rise or fall across regions far larger than any star, larger than any future galaxy. As these ripples were stretched, something important happened. Each ripple grew larger than the distance over which light could communicate at that moment, larger than the horizon of cause and effect. Cut off from the possibility of smoothing itself out, the ripple's shape froze in place. Its peaks and valleys became a record written into the expanding fabric. The small became large, and the fleeting became permanent enough to matter. When inflation ended, the universe was still bright and dense, a hot plasma of photons, electrons, and protons all mixed together. In that light-filled sea, the frozen ripples did not yet grow into structures. Pressure from the light pushed back against gravity. The result was a kind of ringing, sound waves that swept outward from each slight overdensity, compressing and rarefying the plasma in broad spheres. You can picture this as a calm, expanding pulse, like a soft strike on a drum, whose surface is the infant universe itself. As the cosmos expanded, it cooled. After roughly 380,000 years, it reached a turning point. Electrons and protons combined into neutral atoms. The fog of scattering cleared. Light could finally travel freely. The universe became transparent. The sound waves stopped because the medium changed. What remained were slight, overdense regions at specific sizes, fossil spheres left by those ancient pulses. The light that decoupled then has been travelling ever since and still bathes us today as the cosmic microwave background, a cool glow at about 2.7 degrees above absolute zero. In that glow, we see tiny temperature ripples, differences of only a few parts in 100,000, that map the pattern of peaks and troughs set by those sound waves. These small differences were seeds. Where there was a bit more matter, gravity had a slightly stronger handhold. Over time, matter drifted towards these handholds. But not all matter behaves the same. The ordinary matter that makes stars and people can interact with light. before transparency, it was buoyed by radiation pressure and resisted collapse. A different component, dark matter, does not couple to light. It began to gather quietly even earlier, slipping into the small gravitational wells implied by the frozen ripples and forming diffuse, invisible scaffolds. After the universe became transparent, ordinary matter could finally fall freely. It flowed into the dark matter scaffolds like cool air, settling into valleys at night. Over millions of years, those gentle valleys deepened into basins. Basins merged into larger basins, and the first stars were born at the densest knots. Light returned to the cosmic darkness in new form, starlight igniting within structures that had been mere whispers in the beginning. From this process, a web emerged on the largest scales. Long filaments of matter stretched between great junctions called clusters, while vast areas between them remained comparatively empty. The shape of this cosmic web is not random. It reflects the original spectrum of ripples made large by inflation, filtered through gravity's steady work and the push and pull of pressure in the early plasma. When astronomers measure how galaxies are spaced, they find a preferred separation imprinted by those first sound waves, a characteristic distance that repeats like a soft beat in a song. This feature, baryon acoustic oscillations, in formal language, lets us read the growth of the universe's scale with surprising precision. Another quiet clue lies in the near uniformity of the ripples themselves. Their sizes follow a simple rule, not biased toward very large or very small, but close to scale-free, with a slight tilt. This pattern is exactly what many inflationary models predict, and it is what we observe. The faint speckle in the microwave background and the grand architecture of galaxies tell the same story, separated by billions of years, yet matched in rhythm. It helps to keep the sequence in a single, smooth line. First, quantum fluctuations, the unavoidable, tiny jitter in the earliest state. Next, inflation, an explosive stretch that made those jitters into broad frozen ripples beyond the causal horizon. Then in the hot plasma, sound waves rang through those ripples, setting up preferred scales. Transparency arrived, the ringing ceased, the light left to roam and now reaches us chilled, carrying the pattern like an old photograph. Gravity took over, dark matter gathered first, ordinary matter followed. Stars lit, galaxies took shape, filaments formed. The faintest early unevenness became the intricate map of everything we see. You can feel the gentleness of the mechanism even as it shapes immensities. No single hand forces a galaxy into being. There is only slight difference upon slight difference, gathered patiently by gravity across deep time. Where there was a little more kept arriving. Where there was a little less, matter drifted away. The outcome is not brittle, but robust. Change the early ripples slightly, and you change the later web slightly. The melody remains. This story also explains why most galaxies live in company. Gravity's wells are not isolated pits, but connected basins. Matter slides along filaments like water, seeking lower ground, feeding clusters at their crossings. Within those clusters, galaxies dance under mutual gravity. Within galaxies, gas cools and collapses into stars. Around those stars, disks of gas and dust flatten and assemble planets. All of it traces back to the first, almost featureless glow, ornamented only by that faint grain, the ancient ripples made grand. It is natural to wonder how confident we can be. The evidence is layered and consistent. The pattern of temperature and polarization in the microwave background matches the idea of frozen ripples and early ringing. The distribution of galaxies on large scales shows the preferred separation set by those ancient sound waves. The way clusters grow and bend light agrees with a universe where dark matter provides the scaffolding and the expansion history changes over time. Different measures, different epochs, one calm narrative. There is a quiet comfort in this. The universe did not need sharp edges or sudden breaks to become what it is. It needed only a soft beginning, filled with tiny random differences, and the patient pull of gravity. From almost smooth to richly structured, from whisper to chorus, from jitter to web, the path is continuous, and it is kind. Let your breath slow as you hold a single image. Not a lantern, not a storm, simply a pane of cooling glass in which a faint texture appears as it sets. At first, the texture seems trivial, hardly there. Give it time, and it becomes the pattern that catches the light. The earliest ripples of the cosmos were like that texture, subtle, nearly invisible, yet destined, by steady growth and the changing scale of space, to become the scaffold of galaxies. In the next quiet step, we will leave these grand structures and move toward a local extremity of gravity, where light itself can be held to a circular path. The rules that grew galaxies also curve pathways, and near certain depths even a ray of light must go round. For now, rest with the thought that the vast web overhead began as almost nothing, and that almost nothing was enough. Close your eyes and picture a deep, perfectly smooth well carved into the fabric of space. Near the lip of that well, there is a narrow circular track, so finely balanced that a beam of light can run along it in a loop. This track is not a material ring. It is a path in geometry, the only kind of path light ever follows. Around a simple, non-spinning black hole, that circular path sits at what physicists call the photon sphere, a special radius where gravity curves space so strongly that even light can be guided into a circle. In ordinary life, light travels in straight lines. It reflects, refracts, and scatters, but in empty space, it goes straight. Near a black hole, straight is different. General relativity says that mass and energy tell space and time how to curve. And in that curved geometry, the straightest possible paths, called geodesics, can themselves be bent. A photon does not feel a push or a pull in the way a stone does. It simply follows the shortest path allowed by the shape of space-time. Close enough to a black hole, those shortest paths can close into a loop. For a spherical, non-spinning black hole, two distances help set the scene. One is the event horizon, the surface beyond which nothing that happens can ever be seen from the outside. If you like a concrete anchor, the radius of this horizon is 2 times the gravitational constant times the mass, divided by the speed of light squared. For a black hole with the mass of our Sun, that radius would be roughly 3 kilometers. The second distance is the photon sphere, farther out, 3 times the gravitational constant times the mass, divided by the speed of light squared. For a solar mass black hole, that is about 4.5 kilometers. The exact numbers are not the point, the relationship is. The photon sphere sits at 1.5 times the horizon radius for this simple case. This circular track is exquisitely unstable. Imagine balancing a marble at the very top of a smooth dome. In theory, it could sit there forever, perfectly still. In practice, the tiniest breath will send it rolling. The photon sphere is like that. A photon placed on just the right path will circle the black hole, perhaps many times, but the slightest nudge, one more grain of curvature, a whisper of unevenness, sends it either down toward the horizon or out to freedom. The orbit is possible, but it is a knife-edge balance. If the black hole spins, the geometry becomes richer. Spinning black holes drag the surrounding space-time around with them, a gentle twisting called frame dragging. In that twisted geometry, there is no single spherical track, but a family of near-spherical paths. Light that circles in the same direction as the spin can orbit a bit closer in. Light that circles against the spin must orbit farther out. The photon sphere becomes a photon region, a set of allowed circular and near-circular courses whose exact shapes depend on how fast the black hole turns. What would you see if you could hover safely far from such a place and look in? You would not see the photon sphere itself as a glowing ring, because the track is geometry, not matter. But you would see its signature in the way light from the glowing gas around the black hole is bent and focused. Rays that skim near the photon sphere whirl around one or more times before escaping, and these multiply wound rays, pile their brightness into a narrow structure on the image plane, a thin, bright ring. This is sometimes called the photon ring. The Event Horizon Telescope's images of the supermassive black holes in the galaxy M87, and at the centre of our own Milky Way show a blurred orange halo with a darker interior. Within that halo, theory predicts an even thinner, sharper, nested set of rings formed by light that looped many times near the photon sphere before reaching us. Our current instruments blur those fine rings together, but their imprint is present in the pattern. The darkness in the middle of those famous images is not the event horizon itself, but a kind of shadow cast by the black hole. Rays that head inward past a certain critical angle are lost from our view. Rays that graze the photon sphere are bent into caressing loops. Rays farther out swing around only gently. The result is a bright, lensed ring around a dim centre, a picture drawn by null geodesics, which is a calm way of saying the paths of light. Near these depths, familiar effects work together. As a ray of light climbs away from the black hole, it must give up energy to escape the gravitational well, and so its colour is shifted toward the red. This is gravitational redshift. At the same time, the strong curvature focuses some directions and defocuses others, like an exquisite natural lens with no glass. The combination makes the photon ring region particularly bright compared with its surroundings in many models, not because the gas there is uniquely brilliant, but because the geometry funnels many paths into our line of sight. It helps to picture how a single brave photon behaves. Far from the black hole, it travels almost straight. As it approaches, the path bends inward slightly, then more sharply, until, if it arrives with just the right impact parameter, it finds itself rounding the critical radius and turning into a circle. One loop, two loops, perhaps more, and then the tiniest deviation in the initial conditions decides its fate. A hair closer to the black hole, and the photon spirals inward past the point of no return. A hair farther out, and it breaks free, flying to distant observers, and carrying with it the memory of those tight arcs in the form of a delayed arrival and a distinctive position on the sky. Nothing about this violates the rule that nothing outruns light. The circular path exists precisely because light remains the fastest thing. At the photon sphere, straight in the curved geometry happens to be a closed circle. The orbit is not a racetrack that light powers around. It is the shortest available route in a space so curved that the shortest route loops back on itself. There is a quiet symmetry here with the orbits of planets and stars. In Newton's picture, a planet circles a star because gravity provides the inward pull needed to curve the path. In Einstein's picture, the planet is following a straight line in curved space-time, which looks like a circle when sliced at constant time. A photon at the photon sphere is doing the same thing as any free-falling object. It follows the straightest possible path. The only difference is that near a black hole, that straightest path can close into a loop for light, while for slower things, there are families of stable and unstable orbits farther out. These ideas are not only theoretical, we see the fingerprints of strong bending in many ways. Stars that pass behind the central black hole of the Milky Way can have their light slightly magnified and delayed. Flares in the hot plasma near a black hole's edge can show patterns repeating with the characteristic timescale set by the circular photon paths. Across the universe, background galaxies are lensed into arcs and rings by massive clusters, a gentler echo of the same geometry at a grand scale. In each case, light is obedient, tracing the shape of the room it moves through. If you like one more anchor, you can hold a simple timing picture. The time it takes for light to go once around near the photon sphere depends on the mass of the black hole. For the 4 million solar mass black hole at the centre of our galaxy, a lap would take on the order of minutes. For the giant in M87, with billions of solar masses, a lap would take hours. These are not exact numbers, just a sense of scale, and they are comforting. The deeper the well, the slower the circle, the broader the ring. Let the scene calm and settle. The photon sphere is not a place you could perch. It is a property of the geometry, a narrow ridge in the landscape of light's possible paths. It tells us that space, near a black hole, is shaped in a way that permits circles without a track, motion without a road, and images drawn by gravity alone. When we look at the haloed portraits of distant black holes, we are not only seeing hot gas, we are seeing the outline of this ridge sketched in photons that looped and lingered before finding their way to us. Rest for a moment with that thought. In a universe where most paths are open and straight, there are also these rare, perfect loops, allowed by depth alone. Light can be caught into a round, not forever, but long enough to write a ring into the picture and then leave. It is a reminder that geometry can be as gentle as a curve and as decisive as a circle. Next, we will turn from curved paths of light to matter packed into strange, stubborn patterns. The crust of a neutron star, where nuclei crowd so closely that they braid into shapes nicknamed pasta. It is the strongest material we know how to imagine, and it waits in the dark with its own quiet marvels. Settle into a quieter scale, not large but dense beyond imagining. A neutron star is what remains when a massive star's core is squeezed until matter is packed close to nuclear density. Gravity presses inward with a steady, unimaginable patience. The crust responds by arranging itself into patterns that ordinary matter can never make. Near the surface, atomic nuclei form a rigid lattice, something like a crystal. Deeper, the pressure rises and the rules change. Protons and neutrons no longer fit neatly into separate atoms. Nuclear attraction wants to pull everything together. Electrical repulsion between protons pushes back. The two influences balance in a state physicists call frustration, and out of that frustration, shape appears. Those shapes are nicknamed after foods because the images are easier than the equations. There are sheets like lasagna, long tubes like spaghetti, and round droplets like gnocchi. Between these, there are anti-shapes too. Tunnels through sheets and bubbles within slabs are negative of the same patterns. Together, they're called nuclear pasta, not for whimsy alone, but because the geometry truly is a kitchen of repeating forms. Why should this matter be so strong? Strength here is not about hardness to a fingernail, it is about how much strain a structure can bear before it yields. In the inner crust, the pasta forms an interlocked network of nuclei, welded by the strong nuclear force and braced by the star's immense pressure. Computer experiments that track billions of interacting particles suggest that this network resists breaking with a tenacity far beyond anything we know on Earth. Stronger than steel by many orders of magnitude, it is a fabric that does not easily tear. This strength has consequences you can picture. A neutron star spins rapidly. If stresses build in its crust, the pasta can hold tiny mountains on a body only tens of kilometers across. These mountains are not alpine peaks, they might be millimeters high. Yet on a neutron star, even a millimeter's worth of asymmetry can, in principle, radiate a faint, steady ripple in space-time. Observatories that listen for gravitational waves have searched for such whispers. The silence so far sets limits, and the limits teach us about how strong the crust must be. The pasta's presence reaches into other quiet corners of physics. Its shapes can affect how heat and neutrinos travel through the star. They can change how the crust cools after a burst of activity. They may influence the timing of gentle glitches seen in pulsars, those spinning neutron stars that keep time like cosmic lighthouses. None of this is violent in our telling. It is a matter of texture, of pathways through a maze, of how a pattern guides the flow of energy. Evidence is indirect because we cannot reach into a neutron star and touch its crust. Instead, we combine theory, numerical experiments, and the signs nature allows us. The way a cooling star dims, the way a pulsar's rhythm slips and recovers, the absence or presence of certain gravitational wave tones. From these strands, the picture of an ultra-strong, self-organized crust has grown steadily clearer. Where uncertainty remains, scientists say so, then refine their models with care. It helps to keep the sequence simple. Gravity compacts matter until separate atoms cannot keep their distance. Nuclear attraction and electrical repulsion are both strong and cannot both have their way, so they compromise by forming repeating structures. Those structures interlock into a network under enormous pressure, making a crust with exceptional strength. That strength shapes small surface features, controls how the star carries heat, and may, on occasion, leave a distant, measurable trace. Let the image settle. Not a mountain range or a metallic beam, but a quiet, repeating architecture at the edge of a star. Sheets, tubes, and droplets arrayed in patient order, each piece holding the next. In that hidden order lives the strongest material we know how to imagine. When you are ready, we will step back to a gentler vastness and watch gravity's other handiwork. How it bends light into magnifying glasses the size of clusters, drawing duplicate images of faraway galaxies and brightening what would otherwise be beyond our sight. Let your attention soften around a simple idea. Gravity shapes the paths of light. Not with glass, not with mirrors, but with curvature itself. Where mass gathers, space-time bends. And where space-time bends, light follows the curve. Seen from far away, this bending can turn a single background galaxy into arcs, into mirrored pairs, even into a near-perfect circle of light called an Einstein ring. Begin with the quiet rule. In general relativity, mass and energy tell space and time how to curve, and light takes the straightest possible route through that curved geometry. Straight, in this context, may look like a bend. If a massive galaxy or a cluster sits between us and a more distant source, the foreground mass acts as a natural lens. The background object does not change, the space in between does. Light rays that would have missed us are deflected into our line of sight. Other rays are pushed away. The result is both magnification and distortion, a gentle remapping of the background sky. The most striking case is alignment. When the source, the lens, and the observer line up precisely, the lensed image becomes a ring. Its radius depends on three things: how massive the lens is, and how the distances between observer, lens, and source divide the space. You do not need the equation to feel the dependencies. More mass means a larger ring. A lens placed midway, in the broadest sense, bends paths most efficiently. In the sky, these rings are not thick glowing hoops. They're thin, graceful circles traced by many deflected paths from one distant object. Perfect alignment is rare, so we often see near rings, crescents, and long arcs curling around the foreground mass. With slightly broken symmetry, the mapping splits a single galaxy into 2 or 4 distinct images, each arriving from a different bent path. Because those paths thread through different parts of the curved geometry, they take different amounts of time. Light from the same distant flare can reach us first as one image and later as another, delayed by the extra stretch of route and the additional depth of the gravitational well. By measuring these time delays, astronomers can read the expansion history of the universe with a method called time delay cosmography. It is like listening for echoes in a canyon and learning the lay of the stone from the rhythm of the returns. On the largest scales, entire clusters of galaxies act as colossal lenses. Their combined mass, including the dominant dark matter, produces a forest of arcs and multiple images that wrap around the cluster core. These natural lenses serve as telescopes made of gravity. They magnify galaxies that would otherwise be too faint to study, letting us see star formation and structure at epochs not long after the first light of the cosmos cleared the early fog. Some of the farthest galaxies we know were found because a cluster's curvature lifted them into view. There is a quieter version too. When the lens is not a heavy cluster, but a single star or a compact object, the bending is subtle, and the images are too close together to resolve. Yet the combined light still brightens in a characteristic way as the lens crosses the line of sight. This is gravitational microlensing. It has revealed planets drifting around distant stars and, on some occasions, planets with no star at all, worlds adrift between suns. In these events, there is no ring to see, only a gentle rise and fall of brightness that carries the signature of a lens passing in front of a source. Lensing respects an important conservation. Surface brightness is preserved. The lens can stretch an image, making it larger on the sky, and so the total light we collect increases, but the brightness per unit area stays the same. This simple rule helps astronomers model what the lens must be like. By comparing the stretched image with expectations for an unlensed galaxy, they infer the mass distribution of the lens. In clusters, this has revealed the smooth extended halo of dark matter that surrounds and threads through the visible galaxies, a scaffold otherwise invisible to direct sight. If you prefer to hold the geometry with one more image, imagine placing a clear glass marble over a star map. The marble's curvature displaces and distorts the pattern of points beneath. Bright knots stretch into short arcs. Some positions are doubled. Near perfect alignment makes a ring. Remove the marble and the map returns to its usual look. In the sky, the foreground mass is the marble. The background field of galaxies is the map. The difference is that gravity does the refracting without glass or refraction indices, purely through shape. The precision of these effects makes lensing a quiet instrument. Strong lensing, with its arcs and rings, maps mass where it is densest. Weak lensing, a statistical shearing of many faint galaxies, reveals the broader contours of the cosmic web. Time delays between multiple images of a variable source give a measure of distances that depends on the universe's expansion. Microlensing hums along in the background, uncovering compact objects and dark wanderers. All four tunes play together, and each adds a line to the score of how matter is arranged and how the scale of the universe changes. Nothing in this story requires hurry or drama. A photon leaves a distant galaxy and travels on, indifferent to our presence. Near a massive cluster, its path bends a little more with each step, curving gently, perhaps spiraling around the core before resuming its outward flight. Much later, it reaches our telescopes and paints a thin arc, or a faint duplicate on the detector. Another photon from the same source took a different path through the same shaped room and arrives later, a second echo of the same scene. From those paired arrivals, from those stretched and mirrored shapes, the structure of the universe becomes visible without touching it at all. Let the idea rest. Gravity is not only a force that binds, it is also an instrument that reveals. It turns mass into a lens, draws soft circles in the sky, and brings the distant within reach, not by moving it closer, but by guiding more of its light to us. In that guidance is a kind of kindness, a way the universe makes itself legible to patient eyes. When you are ready, we will leave these vast lenses and look for worlds that have no sunrise, planets cast loose from their parent stars. The galaxy may be full of them, drifting in the dark, and even without a ring of light, they leave traces we can learn to read. Let your attention settle on a quiet possibility. Worlds without sunrises, planets that travel the galaxy unmoored, not circling any star, moving through interstellar night on long solitary paths. They are called rogue planets or free-floating planets. Evidence suggests the Milky Way may hold them by the billions, perhaps more numerous than we once imagined, drifting invisibly until gravity briefly betrays their presence. How could a planet lose its star? In young systems, many planets form together, while gas and dust still swirl like a slow storm. Their orbits jostle, giants migrate inward and outward, small worlds gather or scatter. Gravity, patient and impartial, sometimes tips a delicate balance. A close approach between two planets can fling one outward with enough speed to break free. Passing stars in crowded birth clusters can tug at the edges of unstable systems and finish the work. In other cases, a planet may never have been bound at all, condensing directly from a fragment of a collapsing cloud, the way a small dim, failed star forms. The result is the same in our story: a world with no sun to call home. Finding what gives no light is difficult. Here, gravity helps again, in the form of gravitational micro-lensing. When a massive body passes in front of a distant star from our point of view, its gravity gently bends and concentrates the star's light. For a few hours or days, the star appears to brighten in a smooth, characteristic way, then dim back to normal. If there is no luminous host detected, and the brightening is very brief, the culprit may be a lone low-mass lens, a rogue planet. Surveys that watch millions of stars for these fleeting brightenings, patient nets cast across dense star fields toward the centre of the galaxy, have found events that point to a population of such wanderers. How many wanderers are there? The honest answer is that estimates still vary. Early studies hinted at astonishing numbers, perhaps as many or more than the stars themselves. Later analyses suggested fewer, yet still comfortably in the billions. The range remains wide because the signals are brief and rare, and because different masses leave different traces. What is steady is the direction of the evidence. Rogue planets are not oddities. They are a natural outcome of how planetary systems form and evolve. Upcoming observatories designed for wide, precise micro-lensing, space telescopes working in concert with ground arrays, should turn hints into clear accounts. What are these worlds like? Many will be cold. Without a star, the surface temperature of a bare planet would fall toward the deep chill of starlight alone. But not all heat is starlight. Planets carry internal warmth from their birth and from the quiet decay of radioactive elements in their rocks. Massive planets can keep that heat longer. Thick hydrogen-rich atmospheres act like heavy blankets, slowing the escape of warmth to space. Models suggest that a large rogue planet with a deep atmosphere could maintain a temperate layer far above a cold surface, or even keep liquid water beneath an insulating shell of ice, warmed from below rather than above. Moons complicate the picture in a life-friendly way. If a giant rogue planet retains a system of satellites when it is cast off, those moons can be warmed by tides as they flex in the planet's gravity. On Jupiter's moon, Europa, and Saturn's moon, Enceladus, tidal kneading helps sustain global oceans beneath ice even in the distant outer solar system. A similar mechanism could operate in exile. No sunrise would touch such seas. Their energy would be internal and tidal, their nights unbroken, their chemistry slow and steady. It is a gentle thought to hold. Islands of warmth adrift in the dark, supplied not by day but by depth. A rogue planet's sky would be black, punctured by stars that never move much and never rise. There would be no seasons, no familiar cadence of day and night, only the rhythm of weather working with internal heat. If the atmosphere is thick, clouds could glow faintly with scattered starlight. If the air is thin, the stars would be fierce and unblinking. Magnetic fields might still wrap such worlds, generated by churning interiors, the way Earth's field is. With no nearby star to drive a solar wind, the field would interact mainly with the thin drifting gas between the stars, a quieter environment than the one near a sun. Even without direct images, rogue planets leave readable signatures. In micro-lensing, the shorter the brightening, the lower the likely mass. An Earth mass lens may reveal itself over hours, a Jupiter mass lens over days. Sometimes two observatories separated by a large distance will see the same event with a slight shift in timing, a parallax that lets astronomers weigh the lens more precisely. In rare cases, a lensing planet that is not entirely dark, perhaps still warm from youth, can be glimpsed afterward in infrared light. Each technique adds a strand to a growing picture. There are quiet boundaries in naming. Objects more than about 13 times the mass of Jupiter can fuse a heavy form of hydrogen for a time. We call many of those brown dwarfs, not planets, even if they drift alone. Below that, we are content to say planet, whether bound or free. Nature is not obliged to fit our categories neatly, and some wanderers will live in the grey between. The science remains the same. Small worlds to giant worlds, some cast out, some born apart, all sharing the same ocean of night. Why does any of this matter in a calm, sleepy way? Because it completes the picture of planetary systems as living things, not fixed arrangements. Systems form, trade angular momentum, shed members settle. The leftovers roam, knowing that the galaxy holds billions of unlit worlds, changes how we imagine the inventory of places where chemistry can work and time can accumulate. It tells us that the spaces between stars are not empty, but populated by quiet travellers. We only notice when gravity briefly points them out. Let the idea rest as a simple image. Not a lighthouse, not a lantern, just a dark stone moving through cold water, warm at its core, wrapped in its own weather, carrying its story forward without need of a sunrise. The galaxy is full of such stones. Some pass unnoticed, a few announce themselves for a day, all keep going. When you are ready, we will tip from starless night back to the edge of light, where ice hides global oceans and tidal patience keeps them alive. Beneath crusts of frozen water on distant moons, there are seas with no sky above them, stirred by gravity and time, and they wait in the dark with their own quiet possibilities. Let your attention drift to the outer darkness, where sunlight is thin and slow, and worlds wear shells of ice. Beneath those shells, hidden from the sky, several moons keep entire oceans, global, deep and active. They do not need a warm star above them. Their warmth rises from within, from gravity's steady kneading and the quiet chemistry of rock and water. Begin with Europa, a moon of Jupiter, only a little smaller than Earth's own moon. Its surface is a pale sheet, etched with long rust-coloured lines and jumbled regions where the ice seems broken and refrozen. Spacecraft readings tell a simple, astonishing story. A changing magnetic signal, measured as Europa moves through Jupiter's field, fits best if a salty, electrically conductive ocean lies beneath the ice. The thickness of that ice is still debated, perhaps several kilometres to a few tens of kilometres. But below it, models favour a global ocean tens to more than 100 kilometres deep. Salts stain the surface. They likely come from water welling up, freezing and cracking again, a slow, cold circulation between ocean and sky. Why should liquid water exist so far from the sun? Because Europa is not still. It is held in a three-moon rhythm with Io and Ganymede that keeps Europa's orbit slightly stretched. As it circles Jupiter, Europa is flexed by tides. That rhythmic flexing becomes heat inside, friction at the crystal level, warmth in the rock beneath, and subtle melting in the base of the ice. Add dissolved salts, which lower water's freezing point, and an ocean can persist for eons beneath the shell. The ice above may convect like very slow, cold taffy, overturning and carrying surface oxidants downward, a delivery of chemical energy that life, if present, could use. Now turn to Enceladus, a small moon of Saturn, only about 500 kilometers across. It should, by simple thinking, be frozen through. Instead, it breathes. At the South Pole, long fractures, informally called tiger stripes, vent plumes of water vapor and tiny ice grains into space. A passing spacecraft flew through those plumes and tasted their chemistry. Salt was present, showing the water has touched rock. Microscopic grains of silica, the kind that form when hot water reacts with fresh rock, pointed to hydrothermal vents on a seafloor. Molecular hydrogen was there too, a fuel for simple chemistries. Together, those clues describe a dark ocean in contact with warm rock, venting through cracks in the ice into the vacuum, then falling back as snowfall to feed Saturn's faint E-ring, a slow, endless fountain. What would such oceans be like? Imagine a global sea, roofed by ice, floor of rock, where water meets stone at depth, heat and minerals seep into the ocean, making gradients of chemistry. On Earth's seafloors, microbes use those gradients as energy, building communities independent of sunlight. We cannot assume the same elsewhere. We can say the ingredients, liquid water, chemical energy, time, are present in these dark seas. That is enough to make them prime places to study habitability beyond Earth without imagining catastrophe or miracle. Only patience. Europa and Enceladus are not alone. Ganymede, the largest moon in the solar system, shows hints of an internal sea as well, inferred through its magnetic environment and the way its auroras sway. Callisto likely holds a briny layer within. Titan, Saturn's largest moon, has lakes and seas of liquid hydrocarbons on its surface, and strong evidence for a buried ocean of water mixed with ammonia beneath its crust. Even small or distant worlds like Pluto may keep internal layers of liquid preserved by insulating ice and antifreeze compounds. The outer system, once thought to be a deep freeze, turns out to be layered, cold on the skin, lively within. Tidal heat drives much of this activity. You can picture it as steady bending and relaxing, an endless knead that warms ice and rock. A moon's interior responds differently depending on what it is made of and how rapidly its orbit is forced. Some of the heat is focused in the ice shell. Some sinks to the rocky core. Some may sustain a warm, muddy interface where water and stone exchange. Add a little ammonia or salt, and the ocean's freezing point drops. Add pressure at depth and ice forms in exotic high-pressure phases, which can float or sink depending on composition. The result is a layered world with channels for heat and chemistry to circulate. These hidden seas leave their own readable signs. A buried ocean changes how a moon flexes in a giant planet's gravity. Measure that flex and you infer the liquid layer. A salty ocean conducts electricity. Watch how a moon's magnetic environment changes as it moves through a planet's field, and you can estimate the ocean's depth and salinity. Plumes, if present, bring samples straight into space. Sensors can sniff them for salts, organics, and gases that hint at the temperature and rock-water reactions below. Even the surface patterns, ridges, bands, disrupted chaos blocks, can tell how mobile the shell is, and how often ocean water reaches upward to freeze. The timescales involved are soothing. These oceans are not seasonal puddles. Tidal heating can persist as long as resonances hold, and those resonances can last for geological ages. Radioactive decay in rocky cores adds a steady background of warmth. Over such spans, ice shells can thicken and thin, ocean chemistry can evolve, sea floors can fracture and heal. There is no rush. A world can take its time. Future explorers, machines first, perhaps someday instruments that can melt through, will not need to lift whole oceans to the surface to learn their character. A craft in orbit can map gravity, magnetic fields, and ice thickness. A probe that skims a plume can analyze ocean spray without touching the ground. We can begin gently with flybys and surveys, building a picture layer by layer, always pairing technical words with plain images. Flex as warmth, salt as a trail, a plume as a sample lifted to the sky. Let the picture settle into one clear frame, a dark ocean, roofed by ice rising and falling very slowly with the tides, laced with minerals where it meets rock, and sprinkled by flakes of refrozen spray that dust the surface above. No day, no night below that roof, only temperature, chemistry, and time doing what they do. It is a quiet kind of possibility, and it waits in many places. When you are ready, we will step from buried seas to the other extreme of scale, black holes so massive that their event horizons would swallow the paths of our outer planets. The numbers are large, but the ideas are gentle. We will walk them at a calm pace and set them down softly. Lay the solar system out on a quiet table in your mind. Place the sun at the center like a steady bead of light. Set Mercury close, then Venus, Earth, and Mars. Leave a broad ring for the asteroids, then carry your hand outward to Jupiter and Saturn, farther still to Uranus and Neptune, and beyond them the field of cold, dim objects at the edge. Hold that scale for a moment, as if the orbits were thin threads you could lift and measure. Now imagine replacing the sun with a single, deeper object, whose gravity is so complete that light cannot return from within a certain round boundary. This boundary has no surface. It is a radius of no return, a horizon drawn by geometry. For a black hole, that horizon grows in direct proportion to mass. A helpful rule of thumb is simple enough to say aloud in one breath. Add roughly 3 kilometers of horizon radius for every sun's worth of mass you pour in. One sun, about 3 kilometers. A million suns, about 3 million kilometers. A billion suns, about 3 billion kilometers. Translate that into the language of orbits. The average distance from Earth to the Sun is called 1 astronomical unit. It is about 150 million kilometers. Neptune circles at about 30 astronomical units. A black hole of 1 billion suns would have a horizon radius close to 20 astronomical units, large enough to swallow the paths of Uranus and most of the space within. Push the mass to a little more than 1.5 billion suns, and the horizon would reach Neptune's track. At several billion suns, the boundary would extend beyond Neptune toward the Kuiper belt. At 10 billion suns, the horizon would measure close to 200 astronomical units, nudging into the inner realm of the long-period comets. These are round numbers and soft edges, yet the picture is clear. The biggest black holes we know, the ones that anchor bright quasars in the distant universe and sit in the hearts of giant galaxies, would draw a boundary wide enough to hide our planetary family whole. The orbits you placed on the table would fit inside a single dark sphere. Nothing inside that sphere is a flaw. There is no solid skin to strike. Crossing the horizon is like stepping over a line in a field that only the physics can see. Locally, if the black hole is very heavy, the tides at the boundary are gentle. The stretching forces that would tear a person near a small black hole are spread over a much larger scale for a supermassive one. That is one of the quiet surprises of gravity. Make the well deeper and broader, and the gradient at the rim becomes kinder. Outside the boundary, black holes are anything but black if there is gas to feed them. Matter falling inward collects into a flat, whirling disk. Friction in that disk heats the gas until it glows, from radio waves up through visible light and into X-rays, depending on how fast the flow is and how close it spirals before plunging in. When the flow is sustained, the disk can outshine the entire galaxy around it. That is a quasar, a bright, distant beacon powered by a dark engine. The light we see does not come from a surface, it comes from the last frantic circuits of gas on the safe side of the boundary, where gravity is strong and motion is fast. Size changes the tempo of everything nearby. The characteristic timescale near a black hole is set by its mass. For a modest black hole, a few million suns in mass, a tight orbit near the inner edge of the disk might take minutes. For a giant with billions of suns, the same kind of near-edge circuit would take hours, even days. The geometry is the same. The metronome runs slower because the instrument is larger. If the black hole spins, as many do, the boundary becomes flattened, and the surrounding space is gently dragged around with it. Frame dragging is the term of art. A plain picture is a spoon twirling honey, drawing the nearby flow with it. Spin shifts the location of the innermost stable orbits, letting matter approach a little closer on the side that moves with the spin and holding it a little farther on the side that goes against it. These shifts change the efficiency of the engine, tuning how much of the infalling mass's energy becomes light before the plunge. When astronomers speak about the size of a black hole, they're often speaking in units of the horizon radius, counted in those 3-kilometer steps per sun. Telescopes that connect across Earth to act as one, arrays that can resolve details finer than any single mirror, have begun to sketch the luminous rings that form when light from hot gas is bent around these objects. The darker interior in those images is a shadow cast by the hole, the missing paths that fall inward. The diameter of that shadow scales with mass. Measure the shadow, and you weigh the heart of a galaxy from across the universe. The existence of such giants tells a story that stretches back to early times. Somehow, the universe made heavy seeds quickly, perhaps through the collapse of dense gas clouds, without fragmenting into normal stars or through the rapid growth of smaller black holes fed by eager flows. Those seeds grew by merging and by drawing in matter over cosmic ages, turning small wells into wide basins. The largest now live in galaxies with crowded centers, where there is fuel to spare and encounters that funnel gas inward. The giants are not common, but where they exist, they're decisive. It is worth saying what these numbers do not mean. A horizon that could engulf our planets does not reach out like a hand. Gravity decreases with distance. At the distance of Pluto, a 10 billion sun black hole pulls with the gravity you would expect from 10 billion suns gathered in one place, not with any special hunger. If the sun could be replaced by a black hole of the same mass, Earth's orbit would continue, nearly unchanged. The difference is what happens to light and to anything that crosses the inner boundary. The everyday rules of orbits remain friendly outside. Hold the table image one last time. The orbits that felt spacious, Earth's year, Neptune's long circle, are small when weighed against the largest wells the cosmos has built. That does not make our scale less meaningful, it simply places it in context. There are rooms so big that our familiar furniture fits inside the doorway with space to spare. Set the model aside and return to the dark. Somewhere, in a distant galaxy, gas is unfurling into an inward spiral, brightening as it falls. Around the edge of the boundary, photons skim and curve, some looping partway before escaping to tell us what the geometry looks like there. The heart of that system is silence itself, a region that does not answer. Outside it, the universe writes a portrait in light. Let your breath match that slower metronome for a moment. In for a calm count, out for a longer one. The measure of these giants is simple and steady. 3 kilometers of horizon for every sun's mass. A shadow wide enough at the high end to hide the family of planets you know. With that scale tucked softly in mind, we can move on to a colder marvel. A place so chill that it dips below the universe's own background. A natural refrigerator in the dark that breathes out frost into space. There is a place in the sky that breathes out such a fast, thin wind that it chills itself below the background temperature of the cosmos. Imagine cupping your hands near a hiss of compressed air. As the gas expands, it steals warmth and the metal frosts. The same quiet principle unfolds on a scale measured in trillions of kilometers. In the constellation Centaurus, a dying star exhales a torrent so swift that its shroud cools to about 1 Kelvin, colder than the cosmic microwave background's gentle 2.7. This object is called the Boomerang Nebula. Its name comes from early images that hinted at a bent wing-like shape, though higher resolution views reveal a narrow waist and broad opposing lobes, an hourglass of cold vapor. The star at its heart is leaving the red giant stage, entering a brief pre-planetary nebula phase when outer layers are cast off. In this interval, measured in just a few thousand years, the star's lost atmosphere rushes outward and the physics of expansion becomes a refrigerator. The cooling is adiabatic. As the gas expands, it does work against its surroundings, and its internal energy drops, so its temperature falls. No coils, no coolant, only motion and the patient bookkeeping of energy. On Earth, you feel the same law when a spray can turn icy, or when a fog forms in rapidly decompressing air. In the Boomerang Nebula, the valve is a star's open wound, and the mist is a light year wide. How do we know it is colder than the universe's own glow? The answer arrives as absorption. The space between galaxies is filled with ancient light, the cosmic microwave background, that bathes everything at 2.7 Kelvin. Certain molecules in the nebula, chilled by rapid expansion, sit with so little internal energy that they absorb this background faintly at specific radio wavelengths. By measuring how those lines eat a whisper of the background glow, astronomers infer that parts of the nebula's wind are near 1 Kelvin. The gas is not in comfortable equilibrium with its environment. It is cooling faster than the background can warm it. A transient pocket of deeper cold inside a warm sea of radiation. Shaping helps. Many pre-planetary nebulae are not simple shells, but hourglasses and cones, sculpted by hidden companions, or disks that funnel the flow. Collimation, narrowing the outflow into opposing lobes, lets some gas race away faster, cooling more ruthlessly. Dust mixed into the wind can shade inner regions from outside light, slowing re-warming. For a short cosmic moment, all of these influences collaborate, and the thermometer dips toward the floor of nature. This phase will not last. As the central star heats further, its ultraviolet light will seep into the outflow, ionize the gas, and warm the filaments. The boomerang will brighten into a planetary nebula, then fade over tens of thousands of years as the shroud thins and the core settles into a white dwarf. The cosmic refrigerator will switch off, the frost will lift, the background will reclaim its quiet rule. The coldest known natural place is by nature temporary. There is a humility in this scene. The universe carries an ancient warmth, the afterglow of its beginning, and yet a single orderly outflow can locally undercut that warmth without breaking any law. No drama, only timing and geometry. Expand quickly, do work on the surroundings, cool faster than you can be reheated, and for a while you become colder than the very light that fills all space. Hold one simple image as the chapter closes. Not a distant furnace, but a breath that turns to frost in the dark. An hourglass of vapour so swiftly thinned that even the universe's background cannot keep it warm. From this hush of deep cold, we will turn next to the opposite extreme. The first giants, stars so massive and brief that they may have kindled the hearts of galaxies to come. And the clean dark after the first light, most clouds of gas cooled and crumbled into many small seeds, the first ordinary stars. Yet in rare neighbourhoods, the cloud refused to break. It slid inward as a hole, like syrup finding the lowest bowl, and in the centre, a single object swelled. A supermassive star, tens of thousands, perhaps even 100,000 times the mass of the Sun. The recipe is simple to name, if uncommon to arrange. The gas was pristine, almost no heavy elements to help it shed heat. A quiet rain of ultraviolet light from nearby young galaxies broke apart hydrogen molecules, the usual coolant of a newborn cosmos. Without those molecules, the cloud could not fragment easily. Meanwhile, the inflow stayed high, many suns' worth each year, and subtle torques in the rotating gas bled away spin, letting material keep falling inward instead of stalling in a disk. Fed so quickly, the forming star could not contract in peace. It ballooned into a puffy, cool-faced giant. Deep inside, the core was fierce. Outward, the envelope was held up by the pressure of its own light, like wind filling a sail. Brightness and gravity met in a near balance, but the river of gas did not stop, so the star continued to fatten. Its life was brief. In a few 100,000 to a few million years, general relativistic effects tipped the inner balance. The core collapsed, the star fell inward, a massive black hole was born. For a short while, the newborn hole may have worn its old envelope like a cloak, a quasi-star, a hidden engine with a luminous face, until the shroud thinned and the centre stood alone. These heavy seeds matter because of a timing puzzle. We see quasars shining less than 1 billion years after the beginning, powered by black holes already weighing hundreds of millions or even 1 billion suns. Growing so large from small ordinary remnants would take longer than the clock allows, unless growth somehow far exceeded usual limits. Starting with a seed of 10,000 to 100,000 suns softens the climb. There is room to reach those early beacons in time. Where did such seeds form? In dark matter halos just massive enough that gas heated to the point where atomic hydrogen alone could cool it, creating a steady, stable inflow. Often they sat next door to energetic star-forming regions, close enough to bathe the cloud in the ultraviolet light that suppressed molecules, far enough not to strip the gas away. Bars and spirals in the inflowing gas drained angular momentum and fed the centre, large scales handing material to smaller scales in a calm cascade. How might we recognize them across time? They would shine with strong helium emission and little sign of heavy elements, bright but smooth rather than jagged, with many stellar fingerprints. Some candidates with these traits are beginning to appear in deep spectra. Simulations that include gravity, gas, light, and chemistry naturally produce such giants when the right conditions are set. Uncertainties remain, and scientists say so, patiently comparing models with the faintest measurements we can gather. There is a neighbouring path that likely ends the same way. In some halos, the gas may skip the star phase altogether, collapsing directly to a central black hole of tens of thousands of suns. In practice, these routes blur into one another. Both give a heavy seed, born from a steady inflow that never shattered into a crowd. Hold the arc in one breath, a rare metal poor cloud, molecules suppressed by ultraviolet light, spin drained by gentle torques, inflow unbroken, a swollen star, supported by the pressure of its own light. A swift life, a quiet inward turn, a massive black hole left behind to anchor a young galaxy. From a brief giant, a long-lived heart. Set that image down softly, a warm-faced colossus in a clean dawn, fed well, living fast, leaving a centre that guides by gravity alone. The scale is vast, the tempo is slow, and the story is simple enough to keep as you rest. Let the night close gently around what we've seen. A universe that widens as light travels, ripples that grew into galaxies, circles where light can linger, matter braided, strong as stone, worlds adrift, oceans under ice, a breath so cold it frosts the dark, and giants that lived fast and left quiet hearts behind. Breathe in slowly, soften the jaw and shoulders, breathe out longer than you breathed in, and let each thought settle like dust in a still room. Sleep now, the cosmos will keep its watch. Good night, Voyager.